Just start. Welcome to this CMCC webinar on the effects of the COVID-19 lockdown on greenhouse gas emissions. The idea of the webinar is to understand which lessons can we learn from the lockdowns on our way towards decarbonization. We have two excellent speakers. First, Giacomo Nicolini from CMCC IAFES division is going to talk about the effects on CO2 emissions in urban districts. And next, Gianandrea Mannarini is going to complement that talk with analyzing the effect of lockdowns on CO2 emissions for boats and ferries in the European Economic Area. Before we start the webinar, just a short introduction of CMCC. The mission of CMCC can be summarized in three main points. First, to investigate and model our climate system and its interactions with society. Second, to provide reliable, rigorous, and timely scientific results to stimulate sustainable growth, protect the environment, and develop science-driven adaptation. And finally, to develop foresights and quantitative analysis of our future planet and society. CMCC is organized in a network form with offices throughout Italy. And the idea is that this network connects public and private entities working together on multidisciplinary studies concerning issues of interest for the climate sciences in general. We have several members and institutional partners, very well-known ones, for example, Resources for the Future, the Italian Aerospace Research Center, or the University of Bologna, among many others. Furthermore, the scientific organization of CMCC, this network form enhances the integration and collaboration among interdisciplinary skills, which are needed, of course, to deal with climate science-related topics. As a side note, since 2008, CMCC operates its own supercomputer in the University of Salento. This is the only computational facility in Italy specializing in climate change research. And furthermore, we're currently building more computational capacities in our new headquarters in Lecce. Well, of course, all of this infrastructure and scientific output wouldn't be so relevant without outreach. With this in mind, CMCC published plethora of scientific articles for international journals. Also, it gets involved in educational programs, events, communications and disseminations activities for the public at large, for example, like this webinar. Some administrative things, your audio and video are deactivated by default. If you need to intervene or ask questions, you can either write in the question and answer sections or use your raise hand feature, and I will give you the floor when it's pertinent. Some final remarks: the webinar will be recorded and uploaded on the YouTube channel of CMCC. And if you have further questions about the webinar, please just email it to webinar@cmcc.it. And without further ado, I will leave the floor to Giacomo.
Okay, good morning, everybody. As Luis said, I'm Giacomo, and I work at the IAFES division here in Viterbo. Now I will share my screen. Hope everybody seeing it.
Yes, we can see it.
Okay, so I will show you the results from a study we published a few months ago on Journal of Total Environment. And just to, in brief, just a quick insight of what we have done in this study, what we found. So we aim to track the CO2 fluxes over several cities during the first COVID wave and their evolution in the following months. We saw that all sites showed a reduction in CO2 emissions during the national lockdowns. But as the restrictions were lifted, the emission went back to the pre-COVID levels in the majority of the sites. Okay. So there were a few questions we tried to answer in our study. In particular, we were interested to know if there was an emission reduction first, and if yes, of which intensity. Then, if it was related to the stringency of the restriction, if there was a particular time of the day which was more affected by such changes, if the possible reduction was permanent or just limited in time, if this possible reduction was dependent on any particular urban characteristics. And then finally, if there was any kind of agreement between our estimates and those from other independence methods made on broader scales. So we based our study on the ecovariance dataset that, for who doesn't know what this technique is, the ecovariance is a micrometeorological technique that was and it still is largely used in, especially in natural ecosystem. But then in the last 20 years, let's say, it's becoming even more and more popular also in urban environments. It is based on the covariance among the gas concentration in air and the vertical wind speed. And the resulting estimates are continuous data set, continuous time series of data at 30 minutes resolution in general. The basic instrumentation is made by a gas analyzer and a 3D sonic anemometer, which measure the air at high frequency, at least at 10 Hz. And then there is a set of meteorological sensors that produce variables that are used as proxy for fluxes measurements. The ecovariance measure integrates over a certain area that is usually called footprint, the extent of which depends mainly on the wind distribution and statistics, but also on the characteristic of the underlying surface. Okay. In the study, in addition to look at the fluxes, we quantify the anomalies, let's say 2020, according to the relative flux change that was based on taking the fluxes of 2020 and compared with the fluxes of the same period in previous years. We use data from 13 stations all around Europe, and the data sets covered from 3 to 16 years back from 2020. So it's the data set was quite large, let's say. To track the intensity and the dynamic of the measures taken to fight the COVID pandemic, we use the Oxford Response Tracker, and in particular the stringency index, that is a composite matrix that is based on 9 parameters, among which the most important are, for example, school and workplace closures of public transport, and stay-at-home requirements, and so on. It ranges between 0 with no restriction and 100 with maximum level of restriction. According to this index, we defined 4 distinct periods in 2020, and that there was a pre-COVID, let's say, period from January to February 2020, when basically no restrictions were in place. Then there was a lockdown period from March to April in general, and then 2 following periods of 2 months each, in which the restriction progressively were reduced. We analyzed our flux data in comparison to the spatial data. Okay, so we first start with maps, and we consider in each of the 13 stations a certain area. Okay, here you see a circular area because we made an approximation, because we didn't use the actual footprint because its shapes is in general more variable. Okay, but the radius of this area are equal to the median of the 70% flux contribution. That is a kind of a threshold that is generally used in this analysis of the footprints. Okay, so we start with the basic maps of the sites. Then we use also satellite data in this case, for example, we use the NDVI maps to evaluate both the extensions and the intensity of the green areas in each reference area. Then we use the Urban Atlas land use classification to define a number of wind sector, okay, that were as more homogeneous as possible in terms of land use composition, okay, and to each of them we attributed just one class of typology, or one typology. And the main four ones are the residential, non-residential sectors, the sectors characterized by a strong presence of road, and sector characterized by a strong presence of green areas. Then we also compared our data with two independent data sets at city scale that were used to better interpret the area, the flux change at each side. And these two data sets were the carbon monitor emission inventory. In particular, we use the CO2 daily emission from traffic, from vehicular traffic for the years 2019, 2020. And then we use also the Google mobility reports. In particular, we were interested in the metrics relative to the time spent by the population at places of residence. So how did we get here? We first focused on CO2 fluxes time series by comparing the daily means against the daily means of the stringency index. To account for the possible effect, confounding effect of the air temperature, we also computed the relative temperature change. Here you see this in the orange curve. So if we take a city as an example, we first see that the CO2 fluxes started to decrease. You see here the black curve in the, negative values as soon as the restrictions becomes more stringent. Okay, the stringency index is the gray area, is depicted by the gray area. For example, in Florence, the reductions ranged between minus 66% to minus 37%. Then we see that the RFC was not affected in particular by the changes in temperature, because first of all, the anomaly in 2020 of the temperature anomaly of 2020 was not so strong. In fact, you can see the curve that is fluctuating around the zero value. And also, we saw that during the cold days, here you can see the bold part of the curve, the likely increase of domestic heating didn't impact so much on fluxes. Then we also noticed that when measured the stringency or the measure started to decrease, also the flux anomalies started to return to, let's say, usual values. Okay, you can see here the curves that converge basically. Okay. So by looking closer to the relationship between the RFC and the stringency index, where here the flux change are grouped by stringency index of 10 points width, we found that basically at all sites had a significant reduction of emissions during the most restrictive measures. Okay, so if we take again two districts as example, we found in general that the reduction reached its minimum, that is, let's say, less than 50% of reduction under the highest stringency index value, above, say, 70. But some cities showed a clear and consistent decrease in RFC with stringency index. For example, Heraklion, it's one of these kind of districts, while others, although the relations was still clear, showed a more variability, okay, hinting a more complex situation in which other drivers contributed to the emission reductions. When analyzing all districts together, here we see that each dot represents the average RFC and SC for each period in each district. The correlation become evident. And also here is visible a kind of hysteresis in the data, where in the period before the restriction, here in gray, the average RFC was not significantly different from 0. Then reached a value of, on average among sites of minus 36%, and then started to decrease back to minus 17 in the post-1 period, and then to minus 7 in post-2. Then, apart from the relative flux change, we look at the dial patterns of CO2 fluxes. Our data sets allowed for this, given the high resolution. And here we see the dial fluxes of each period measured in 2020 in the red curves against those measured in each of the previous year, the gray curves. If we focus on 2 districts again, we see that the dial pattern of the CO2 flux in different districts fall into 2 main categories. A bimodal emission patterns typical of the district where EV traffic is present. So you can see here, for example, in the Pesaro case, the 2 peaks during the rush hour periods, in the morning and in the evening, and a monomodal pattern with a single maximum at midday, typical of cities where the activity is more spread all over the day. So we found significant reductions of CO2 flux intensity in all districts during the lock period compared to the previous year, that on average varied between minus 10 to minus 63%. And in all cases, the reduction occurred mainly during daytime, except for some cities like, for example, Vienna or Amsterdam, and London, big city, where restriction had a certain effect also at night. Then the partial lifting of the restriction period led to a general recovery of the emission, which reached their baseline level during post 2, basically, at the 4 months after the end of the lockdowns, in 9 out of 13 districts. To investigate then on the role of the urban characteristic in the emission reduction, we analyzed the CO2 relative flux change as a function of the district land use and lockdown period. Okay, so if we focused on, again, two other examples, we see that the wind sector that characterized by non-residential area and also by the roads showed the largest emission reduction during the lockdown period in all cities. You see here the red bars, the second and third columns. Emission reduction and recovery in the residential area was instead less consistent among sites, following different dynamics. This was likely due to the pandemic-related changes in vehicular traffic and emission associated with, for example, domestic heating or cooking, which are function typical of the population density and other specific characteristics of each district. Then also the recovery rate was not the same among the districts. Indeed, a quicker emission recovery was experienced in the non-residential sector already after the starting of the post-1 period, while in other land use types, the reduction persisted, at least in part, during the recovery phase. Finally, when we compared our estimates with those from independent city-scale course inventory data, we still found common dynamics. For example, despite difference in the spatial scales, there was a clear link between the reduction in road traffic emission estimated by the carbon monitor method using the traffic congestion data. These are model data at daily resolutions. And lower measure the CO2 emission in the road, residential and non-residential sector in all cities during the lockdown. You see here, all the data are placed in the third quadrant of the plot. Then during the post-1 period, that is soon later the lockdown, the correlation progressively decreased and disappeared totally during post-2, when the traffic emission according to the carbon monitor are close to pre-pandemic level, basically. In residential area, we filter the data considering the sector with less than 20% of road to avoid the influence of the traffic on this analysis. The CO2 emission did not increase significantly during the lock period, despite an average 20% increase in time spent at home, according to Google. And this suggests that vehicular traffic can be the main factor driving the CO2 fluxes in the monitored districts, and emission from eating, cooking, and human respiration playing a lesser role in this case. So, wrapping up, hoping you'll see there. Assuming the specific conclusion, we saw that at all sites, CO2 emissions were significantly reduced during the strictest lockdown measures. But for most city sites, the CO2 emission returned to pre-pandemic levels by autumn 2020. The emission reduction occurred mainly during the daytime, principally as a consequence of limitation on mobility, and in particular, the reduction on vehicular traffic. While emission related to home confinement did not increase enough to compensate for the reduction in emission from road traffic. The substantial emission reduction recorded through the first COVID pandemic wave was temporary in most of the city district, and emissions rebounded to the previous levels once the restrictions were eased in the following months. From a broader point of view, we can say that this study highlighted the additional advantage of the monitoring networks, where data collected from individual stations can be synergistically combined for long-term monitoring activities. As an example, the ICOS integrated, the ICOS is the integrated carbon observation system where I work for. And I just want to recall that the data that we process are fully open and fully available to everybody. Then that the covariance method is a valuable tool for monitoring continuously and almost in real time the short and long-term change in urban trace gas emissions, and consequently for assessing the effectiveness of climate change mitigation policies. For example, say limiting traffic emission versus reducing building, heating demand, and so on. Our results also demonstrate that altering the human behavior has a direct and immediate and significant effect on the reduction of urban CO2 emissions. But however, the temporary nature of the reduction emphasizes the need to implement a systemic change in the city ecosystem and in people's lifestyle to achieve effective and sustained climate change mitigation. Okay, so all the data we used and the code we use for this analysis are available here in these links. And then here is the paper where if you are interested, you can find details on data processing, statistics, and other more interesting numbers. Thank you.
Okay, excellent. Thank you very much, Nico. Giacomo, very interesting presentation. Now I leave the floor to Gianandrea.
Hello, thank you, Luis. Let me share my presentation, which I believe is on your screens now. And yes. Okay, thanks. And I'm a researcher at the Ocean Predictions and Applications division in Lecce of CMCC. And let me say that I'm very much in debt for this work to my co-authors, and especially to Mario Leonardo Salinas, who made most of the numerical computations, and Professor Alessandro Fassò from the University of Bergamo, who devised the theoretical framework with us. Well, in this brief presentation, I would like to speak about the impact of COVID-19 lockdowns on maritime transport and ferries in particular. And this topic has been investigated by several authors to date, and it even found a place on journals traditionally devoted to the investigations of fundamental properties of nature, such as Scientific Report and Nature Communications. So this is a signal for me that human activities now are taking a very important place in the scientific community. And in particular, what these reports found was that, as we would expect, shipping was affected by what happened after the outbreak of the pandemic in 2020. And in particular, a reduction in port calls for several sectors of shipping was observed, especially for ships carrying passengers, which makes sense, of course. By using mobility data, several scholars assessed the reduction in navigated miles in 2020, and it was even possible to assess a relationship or a correlation with the lockdown stringency index already mentioned in the previous presentation. As ferries are concerned, we expect a big impact on their activities coming from the lockdowns, since they carry people, not just vehicles. And also ferries are quite relevant for emissions, since, for instance, in Europe, in the European Economic Area, they represent 3% of the fleet, but they account for 9% of the CO2 emissions. So their importance is over proportional. So our research questions were somehow similar to the one mentioned in the previous presentation, but of course they had to be rescaled to the actual data availability. And this is a point I will make several times in my presentation. Data availability for maritime is not as accessible and as easily accessible as for terrestrial data. So basically, we were curious about knowing more about the changes in the emission patterns from ferries in Europe, if these changes were related to specific fleet features or to the to the sea where these ships were sailing. But also, I would say, we were curious about the difference about what happened to the total CO2 emissions from these ferries, and the emissions occurred at berth. So the emissions while the ferries were at in the harbors, in the ports, and this is of course relevant for human health, since these emissions usually occur closely to densely inhabited areas, while the total emissions matter for their climatic impact. So let me say something about the data, the input data we used. Basically, we had two distinct data sets. One was open and was provided by EMSA, the European Maritime Safety Agency, through their FETIS MRV system. This is a system which EMSA has put in place in order to be compliant with the European regulation and to support the European Commission in spreading this data collected by virtue of the Regulation 757 of 2015. So the important piece of information about this data is that the published version of this data is aggregated on an annual basis. So this data is monitored on a voyage basis, is collected and stored on that resolution, but then aggregated for for publication. This means that forget about the nice intra-annual and even intra-dial patterns shown in the previous presentation. Here we are speaking about having basically one number per ship per year. And we have 3 years only, since the first data were available for 2018. So we had 2018, 2019 before COVID, and 2020 at the time this study was conducted. But the good thing is, as I was saying, that there is a distinction between the total and the at berth component of these CO2 emissions. And there is also information about the monitoring methods. Here again, in most cases, it is not direct CO2 emission measurement. I would say that up to 2020 for ferries, this was never the case. So it was always through some proxy of emissions that these emissions were, say, measured, such as the amount of bunker delivered to the ferry, or the data coming from onboard flow meters. Okay, so this is the open source part. Then for the restricted access, we purchased a bespoke data set by IHS Markit, which is now a part of Standard & Poor's Global. And this data set included information about vessel characteristics, such as size, engine size, propeller, passenger capacity. And also we purchased the data about the some activity data of these vessels, specifically the timing and location of the port calls. This port call information we used mainly for georeferencing in an approximate way the emissions, since this was not part of the EMSA dataset. So we attributed a ferry to one of these 3 European sea domains, the North Sea, the Baltic Sea, or the Mediterranean Sea, depending upon where the vessel made most of her calls in a given year. And this is, I think, for 2020, the data in this table. So as you see, the North and the Baltic Sea altogether, they account for nearly the same number of vessels sailing in the Mediterranean Sea. And in total, we have about 300 vessels. Here, by vessels, I would like to specify that I mean, in particular, not high-speed crafts. This is relevant to some extent, since if you consider the fleet of ferries sailing in the European Economic Area, you will see, for instance, from this scatter plot, that it clusters quite naturally into two subgroups. And the one on the right-hand side of this plot corresponds to the high-speed crafts. And it has been suggested by various authoritative sources, such as Ferry, for instance, that these high-speed crafts should not be considered altogether with displacement ferries, because I mean they have completely different power and speed characteristics. So we focused just on these non-high speed ferries or displacement hull ferries. And from this plot, you see that their main engine power basically scales with their top speed. Here we report the speed in a normalized version called Froude number. But also it's interesting to see that for each given service speed or Froude number, there is a broad variability in engine power, reflecting the various size and the passenger capacity of the vessels. In general, the trend is that newer ferries are larger and carry more passengers and are faster than older ones. So I need one extra slide about this ferry type, since this is going to be crucial in the following of this analysis. So out of the many ways to characterize this ferry population, we restricted ourselves to just a few parameters, and specifically the power of the main engines, the number of passengers, the maximum number of passengers, the length overall of the hull, and the year of build. So we found these four parameters were quite powerful in classifying the existing fleets. And also we decided to further simplify our approach by having so-called dichotomic variables. It means that we discarded the full information about the values of these four parameters and just checked if they were below or above a specific threshold set at the median of the distribution of these values within the fleet. So just to be concrete, to have a ferry to have a large engine for us meant that its engine power was above about 21 megawatt. Having many passengers for us was having more than 1,250 passengers, and longer hull meant longer than 174 meters, and a new vessel meant built after 1999. So if you have these four dichotomic variables, all possible ways to combine them is 2 to the 4th, that is 16. So we subdivided the fleet into these 16 subclasses, of which you see one exemplar, one individual in these pictures below. So in a rough way, from the left to the right, we move from older, smaller vessels to newer, larger, and more powerful vessels. Okay, some descriptive information before we go on. Just using an Excel sheet, you can compute some basic statistics about what happened in 2020 compared to 2019 and also 2018. So the key numbers, just to have a feeling, is that total emissions per ship were in the order of 30-40,000 tons, while at berth emissions, so the emissions while the vessel is in the harbor, were some 1/15 of this value, so a bit more than 2,000 tons. Just to have a feeling, a typical Italian citizen is responsible for about 6 to 7 tons CO2 every year. And from these very simple descriptive statistics, you can find that at median level, these per ship values changed by about 15%. So the total emissions in 2020 were 15% lower than in previous year. While for the emissions at berth, this reduction was lower, about 6%. There is a bit difference if you move to the mean rather than the median averages. But so say we have decreases in 2-digit size for the total emission. This is the first take-home message, and also for the number of port calls. There is, however, a broad distribution, as you see from these violin plots here. And this drives me into the next point, which is the fact that this descriptive approach you can work out with a simple Excel sheet is clearly not enough if you are interested in assessing any causal relationship between the COVID outbreak and the changes occurred in the emissions. Just to be clear, the emissions before 2020 were on the growth. Several scholars made this point. So as you want to assess the causal impact of COVID, you should account for this effect somehow. Also, if you remain at the level of descriptive statistics, it won't be possible to assess something which in statistics is very important, and it is the uncertainty. So we are always sampling a limited population, so we should be able to put some error bar next to our numbers. So this is why I was not giving too much importance about the 15-19% decrease in previous slide. We need to go to a more sophisticated level of analysis. Basically, in statistical jargon, this means that you need a proper modeling of the error structure in your data. And in order to assess causal relationship with COVID, you need some model where your covariates, so your independent information, independent variable, interact with some COVID-related variable. So all these features correspond. You know, when in textbook you find the proposition that you do linear regression under the hypothesis that you have independent, uncorrelated, Gaussian distributed errors, and so on. You say, okay, this is given. Let's go on. Well, if you accept this in this case, you would commit an error, because in this actual case for this data set, this assumption is not given. In particular, the data of the emissions from these ferries across the various years are strongly correlated. There is a strong temporal correlation. And if you neglect it, you end up with, you can go on with your machinery, computing all your statistical tests, but then the significance, so the p-values you compute will not be very reliable. So this is why we resorted to what is called the linear mixed effect modeling with the interaction. So the mixed refers to the fact that we have this so-called random term in violet in our regression.
Gianandrea,
yes.
Sorry, you have 4 to 5 minutes to leave 10 minutes for questions, just to let you know.
Yes, thank you.
No worries.
So I will accelerate here. So we tested several combinations of models, of predictors specifically, combinations of vessel type, sea domain, with COVID, with the number of port calls and so on. And it ended up that the best model was a regression like this one, where COVID was basically a dummy variable, which is 1 in 2020 and 0 before 2020. So let's go to the results, which are basically the estimation of the effects from this model. And they provide a few information. The first one is that COVID, that is 2020, the year 2020, led to a statistically significant reduction in total emissions, but not for the emissions at harbor. This is not statistically significant. Then we found that the high passenger capacity ferries experienced the larger and statistically significant reductions, and that the North Sea ferries had an extra reduction with respect to both the Baltic and the Mediterranean Sea ferries. As the emissions at berth are concerned, we found both vessels type with a decrease in emissions, such as the category 11, and vessel type where the emissions increased. This points out to the fact that possibly different practices were used, both so-called cold and hot layup of these vessels while in port. So here I'm shrinking this, but I would like once more to make the point that data availability is quite restricted for this maritime data, but the EMSA data is definitely a good progress on this. We hope if there's any policy or decision maker listening here or in future listening to the registration, that some effort will be done for making also the per voyage basis data available. This would help a lot the research, but I think also the policy community for verifying the data reported. Our work is totally open source. We published the data set generated from augmenting the EMSA data with the commercial ones from IHS. Even the source code is open and available on GitHub. And just to conclude and recap, the main answers to the research questions, the number, you will find the number in the paper, of course, but the message is that high passenger capacity, all the ferries were the most impacted category by COVID as CO2 emissions are concerned, and that emissions at berth did not change significantly, but there is some suggestion, some indication from the data that diverse layup practices were used. So some vessels were probably, say, switched off completely during 2020, while others remained active and making even more emissions in port than before COVID because they didn't sail. As an outlook, we believe with my co-authors that the approach is some degree of generality. So we are quite positive and confident it could be used also for other outcome variables, not just for CO2 emissions. For instance, there are some carbon intensity indicators or energy efficiency within the EMSA dataset, which could be interesting to explore. It would be interesting to explore the 2021st rebound, if any, in emissions, as well as applying this methodology, this statistical methodology, to investigate other macroeconomic shocks, such as Brexit, or the war in Ukraine, or global crisis and other similar effects, for instance, impacts of climate change. Sorry, I'm done. Thank you very much for your attention. I'm looking forward to your question.
Perfect. Thank you very much, Gianandrea. If you can stop sharing the screen, perhaps. Okay. Excellent. So we answered already some of the open questions in the chat, but just to keep things going, I will start with some questions of myself, perhaps one for Giacomo, one from Gianandrea. Giacomo, I was wondering, you said that these data sets come from a universe of stations. What was your reason just to choose the stations that you chose?
Because there are in the big network, there are not so many stations that measured fluxes over urban environments. Okay, they are there, but are still not so much. Okay. So we reached these teams by either by personal contact, or because they already published their data on other networks.
Okay.
So we reached them directly, taking the chance of a PhD working with us.
Okay.
And then we start sharing the data.
And do you have any intuition? I think you said that from all the districts, I think 3 didn't rebound back to the level. Do you have any intuition on these 3? Perhaps why didn't they rebound? Was it like policies, like reducing traffic afterwards, or what was it?
Yes, for example, one of these cities was Amsterdam, for example.
Yes.
And the district that we analyzed was characterized by a strong presence of tourists.
Okay.
So, for example,
so they didn't come back.
Yes.
Okay.
Not yet, even after 4 months.
Very interesting. Yes. Very cool. And sorry to interrupt you.
No. And now we are working on a follow up of this study, taking the chance of having the data up to basically last month. So we are trying to track all the 21 and even the 22 flux dynamics.
Great. Yeah, that will be very interesting.
Hopefully.
Gianandrea, while your presentation, and also I went through your paper, well, there is a strong reduction, right, in CO2 emissions coming from boats based on your research. There's this new study also in the US showing that boats are not only very intense in terms of CO2, but also very intense in terms of air pollution. Do you have any intuition or any papers that have looked at this effect of the COVID on not only CO2, but air pollution, and how this can affect the people living close to the ports?
Well, thank you. This is indeed quite relevant. It is unfortunately, this data is unfortunately not part of what published via the TETIS MRV system of EMSA. There is, we can assume that to some extent the CO2 emissions are a proxy of some other noxious emissions and particulate matter emissions, though some of them will depend on the details of the propulsion system and so on. But I think we found some paper in our assessment of the literature, and most of them were not using direct measurements, but mainly bottom-up reconstructions of emissions. I would be very interested indeed to have some direct observation as for the terrestrial data.
Yeah, very interesting. Well, there was one question by Yasir, but I think because we have two presentations, the time for questions was shortened and people are starting to leave for lunch, I believe. But anyhow, if anyone has any questions, please raise your hand and I will give you the voice. If not, well, I think both papers very interesting, very well connected. Perhaps a lot of space for collaboration in the future between the two group of authors. And
maybe yes.
Yes. Also, I will write you emails. The economists over here to try to get your data.
Be very welcome.
But okay, very interesting, very nice, and thank you very much. And with this, I will close the seminar. And well, have a nice lunch.
Okay, thank you everybody.
Okay. Take care.
Bye.
Bye.